Okay, so welcome to this next video in which we are discussing the epidermis. Okay, right, so we're currently in the process of discussing the basement membrane, also known as the basal lamina, and we've seen that basement membranes can be divided into two layers, the lamina densa and the lamina lucida. Okay, right. We are currently studying the lamina lucida, which remember is the one which actually is underneath the basal keratinocyte layer. Okay, and we've discussed that the lamina lucida is made up of this network of heterotrimeric laminin proteins, which are made up of three separate subunits, an alpha laminin, a beta laminin, and a gamma laminin. And each of these three subunits of a heterotrimeric laminin has a laminin N-terminal domain, and it's these laminin N-terminal domains which combined to the laminin N-terminal domains on other heterotrimeric laminins. Okay, specifically three of them can come together, and this will form a network of tessellating hexagons. Okay, and it's this which is the lamina lucida, basically. The lamina lucida is a layer of these tessellating heterotrimeric laminins, where the laminin N-terminal domain tessellating hexagon network is facing the lamina densa, okay, and all of the coiled domains with the 5 laminin G-like domains that are sticking up from this network are then facing the basal side of the basal keratinocytes. Okay, and what we now want to discuss is how these basal keratinocytes are going to bind to those 5 laminin G-like domains of these laminin heterotrimers here. Okay, and this is going to be through integrins. So let's now discuss integrins then. Okay, so basically integrins are made up of two separate proteins. Okay, so let's show these here. So they're made up of an alpha integrin and a beta integrin, and we're going to see, this isn't the end of us seeing alpha and beta, basically. Okay, so here we have our alpha integrin here, okay, and this is the amino terminus, and this is the carboxylic acid terminus. So alpha integrins are polypeptides which have a single membrane spanning alpha helix. Now the amino terminus will be facing the extracellular fluid, so this is the extracellular fluid side, the ECF side, whilst the carboxylic acid terminus will be facing the cytoplasmic side, so this is the cytoplasm here. Okay, and what's going to happen is alpha integrins are going to bind to another type of integrin known as a beta integrin. So integrins overall are made up of these heterodimers, which consist of an alpha integrin bound to a beta integrin. Okay, here's the amino terminus, and here's the carboxylic acid terminus. Okay, so the whole thing then consisting of both an alpha integrin, which is now coloured in vivid purple here, and a beta integrin coloured here in green, that then is called an integrin. Okay, so it's a heterodimer of two separate subunits, basically. Okay, now integrins are what are known as cell adhesion molecules. Okay, so let me just talk a little bit about cell adhesion molecules. So cell adhesion molecules are often abbreviated as CAMs for short. Okay, C for cell, A for adhesion, and then M for molecule. Okay, and they're involved in binding two cells together. However, there's two ways that you can do this, basically. Okay, one way that you can bind two cells together is what's known as the direct interaction between two cells, or indeed as a cell-cell interaction. Okay, so you'll have your two cells here, and basically on the surface of cell 1 here, you'll have your cell adhesion molecule. Okay, so this is cell 1, and on the surface of cell 1, you have a cell adhesion molecule here, such as, for instance, integrins can form direct interactions, but it's much rarer than the type of interaction we're going to see. Okay, but there are other types of cell adhesion molecule as well. Okay, so basically on the surface of the two cells, you're going to have these cell adhesion molecules. Okay, so both cells will have a cell adhesion molecule on their surface, and the two cell adhesion molecules are going to bind together. Okay, this is known as a direct interaction. Okay, so this is a cell-cell interaction. And this is one of the ways that cell adhesion molecules can hold two cells together. So this is a cell adhesion molecule. Okay, the other way that cell adhesion molecules can hold two cells together is the indirect interaction. Okay, and this is basically when the cell will have a cell adhesion molecule on its surface, but this cell adhesion molecule isn't going to bind directly to another cell adhesion molecule on the surface of the cell that we want to bind to. Instead, what it's going to do is it's going to bind to some component of the extracellular matrix, which I'll show here in green. Okay, so this green fiber here, this is some component of the extracellular matrix. Okay, and for short, I abbreviate extracellular matrix often to ECM, but I think I should write it out at least once. So the E is for extra, the C is for cellular, and then the M is for matrix. And basically, the cell adhesion molecule binds to a component of the extracellular matrix, and then the cell adhesion molecule on the other cell is also going to bind to that same extracellular matrix. Okay, like so. So it's also going to bind to the extracellular matrix, and hence you're going to indirectly link the two cells together in this way. Okay, so this is an indirect way in which cell adhesion molecules can link two cells together, and this is known as a cell matrix cell interaction. Okay, so integrins, the main type of cell interaction that they're going to produce, the main type of adhesion between two cells that they're going to produce is going to be through these cell matrix cell interactions. Okay, so basically the integrin heterodimer here of the alpha integrin and the beta integrin, this is analogous to our blue blob here. This is our cell adhesion molecule. It's then going to bind to a component of the extracellular matrix. Then that component of the extracellular matrix might be linked to other components of the extracellular matrix, and then those other components of the extracellular matrix will then attach to a cell adhesion molecule on another cell, and hence you've indirectly linked those two cells together. Okay, right. So there are four major families of cell adhesion molecules. Okay, and there are other families of cell adhesion molecules out of the four main families. But I'm going to tell you about the four main families. I'll tell you about some other little smaller families of cell adhesion molecules that we will come across later on in this video. But the main four families of cell adhesion molecules are firstly the integrins. Okay, so these are the ones that we're currently interested in because these are going to be on the basal membranes of the basal keratinocytes, and they're going to be involved in binding to those 5 laminin G-like domains of the laminin heterotrimers. Okay, so integrins are a type of cell adhesion molecule. Okay, then another major family of cell adhesion molecules are the cadherins. We will come back to the cadherins later on. These are going to be very important when we want to discuss desmosomes. Okay, and desmosomes are going to be important in the skin. Okay, the other two big families of cell adhesion molecules we're not going to see in this video. Okay, they're very important in the cardiovascular system. Okay, they're the selectins. Okay, and also what are known as the immunoglobulin superfamily cell adhesion molecules. Okay, so the selectins includes things like P-selectin and E-selectin, which are extremely important in the recruitment of leukocytes to sites of inflammation. Okay, immunoglobulin superfamily cell adhesion molecules, okay, which I'll just abbreviate to CAMs. These are extremely important again in the recruitment of leukocytes, white blood cells, to sites of inflammation. Things such as ICAM1, VCAM1, these are all immunoglobulin cell adhesion molecules. PCAM1 is another example of an immunoglobulin superfamily cell adhesion molecule. And for short, the immunoglobulin superfamily cell adhesion molecules are often abbreviated to the IGSF CAMs. Okay, so IGSF is short for immunoglobulin, that's the IG. SF is superfamily, and then we've got cell adhesion molecules, which is the CAMs. Okay, so we at the moment are going to focus on the integrins. Oh, and I was just going to tell you about a few more niche families of cell adhesion molecules. So these are the big four. Okay, these are the ones that people usually quote when they are telling you about the cell adhesion molecules. Other families of cell adhesion molecules, which we will come to later, are, for instance, the claudins, okay, the occludins, okay, which only actually includes one protein for our purposes, which is occludin, okay, and then finally also the junction adhesion molecules, okay, which are known as the JAMs. Okay, so we will come back to the claudins, the occludins, and the JAMs later on when we come to talk about the tight junctions that are also going to be important in the epidermis. Okay, right, so those are cell adhesion molecules then. Okay, so let's focus in on the integrins then now. Okay, so we've said that integrins consist of these two proteins bound together. They consist of an alpha integrin with a beta integrin. Now, there are many different alpha integrins and there are many different beta integrins, which gives you the scope to create a huge number of different heterodimers and therefore a huge number of different integrins. Okay, right, so just how many of each type of integrin are there? Well, there are 18 different alpha integrins, okay, and then there are 8 different beta integrins, and I just want to tell you about the naming of these 18 different alpha integrins and the 8 different beta integrins. Okay, right, so let's start off with the 18 different alpha integrins. Okay, right, so the first 11 are named very sensibly. Okay, so the first 11 are just called alpha 1, alpha 2, alpha 3, all the way up to alpha 11. Okay, so those are the first 11 alpha integrins. Okay, then let's do the next 7 alpha integrins. Okay, so the next 7 have sillier names, okay, but they're not too silly. Okay, you then have alpha D, okay, alpha E, alpha L, okay, alpha M, alpha V, alpha 2B, and then also alpha X, okay, and these make up the final 7 alpha integrins. Okay, that takes us up to 18 in total. We have 11 here underlined in green, and then we have 7 here underlined in purple, and that takes us up to overall 18 different alpha integrins. Okay, right, now let's talk about the 8 beta integrins. Okay, so the 8 beta integrins, these have a very simple naming system. So they are just called beta 1 through beta 8. So you have beta 1, beta 2, beta 3, all the way up to beta 8. Okay, and that completes the 8 different beta integrins. Okay, right, so those are the different alpha and different beta integrins. So, in total then, how many different heterodimers would it be possible to construct? Well, there are 18 different alpha integrins that you can use in this pink socket here, and there are 8 different beta integrins. So how many overall integrin heterodimers does that mean that there are possible? Well, that means that there are 18 times 8 that are possible in total, and that's 144. Okay, so 8 times 10 is 80, 8 times 8 is 64, add those together, 144. Okay, you do not actually find all 144 present in the human body. Okay, in actual fact, we have only found 24 of the plausible 144 combinations present within the human body. Okay, now, interestingly, of these 24, 23 of them bind to actin within the cytoskeleton, and one of them binds to intermediate filaments. Okay, so let me just talk then about the cytoskeleton and what this actually all means. So, what are these integrin molecules actually going to do? We've discussed them as transmembrane proteins, but what are they actually going to do? Why am I discussing these? Basically, these integrin heterodimers are going to bind to the 5 laminin G-like domains of laminin heterotrimers, basically, which, remember, are pointing up towards the basal keratinocytes. Okay, so to give you the picture then, we've got our basal keratinocyte here. Okay, we've then got our laminin heterotrimer here. Okay, and let's colour in our laminin heterotrimer. Okay, so we've in red here. Here are the laminin N-terminal domains. Then we've got our coiled coil domain in turquoise here. And then we've got our 5 laminin G-like domains in orange here. And basically, on the basal surface of our basal keratinocyte here, and I'll give it a nucleus to make it look more normal, we're going to have certain integrins which are going to be fantastic at binding to the 5 laminin G-like domains of the laminin heterotrimer. And this is how the basal keratinocytes bind to the lamina lucida, by binding to these 5 laminin G-like domains of the laminin heterotrimers. Okay, now, what else does the integrin bind to? Because at the moment, this is not a very strong adhesion. What I've described to you is not going to be a very structurally sound thing to do, okay? Because all you are attaching to, you're attaching your laminin heterotrimer to the cell membrane of this basal keratinocyte. Now, the cell membrane is just a flexible gloop, okay? So this is not a very structurally sound thing to do, okay? So what you would really like to do is attach this these 5 laminin G-like domains of the laminin heterotrimer here to the rigid structure within cells. Now, what is the rigid structure within cells? Well, let's now discuss the cytoskeleton. So basically, when we draw a picture of cells, we usually draw something that looks like so. Okay? We draw our cell membrane here with our nucleus inside. Okay? Now, this is a nice picture, but it's not very realistic. In actual fact, the cytoplasm is full of a nightmarish meshwork of proteins. So basically, inside the cytoplasm, you have proteins going all over the place. Huge, great protein filaments all over the place. So if we were actually to draw this, the cytoplasm is full of this meshwork of proteins, and this is rigid, this is strong, this is why cells remain in a constant shape. This is what holds the plasma membrane up. It holds it in the continuous shape of the cell. This is what is actually holding the cell in its structure, basically. Okay, this is the rigid structure within cells, and this is called the cytoskeleton. So this rigid meshwork of proteins all over the place, this is called the cytoskeleton. Okay, now if we want a structurally sound connection between the extracellular matrix in the form of these laminins, and these laminins are considered a component of the extracellular matrix. Okay, if we want to link the extracellular matrix to something structurally rigid within the cells, then we need these integrins on their cytoplasmic side to link to the cytoskeleton. Okay, right. Just also to go back to the fact that these integrins are cell adhesion molecules, okay, coming back to this cell matrix cell interaction, the integrin is the cell adhesion molecule, okay? It's going to bind to a component of the extracellular matrix, which is our laminin heterotrimer here. The laminin heterotrimer is then going to go and bind to another laminin heterotrimer, for instance here. Okay, so let's colour this in. Here are the laminin N-terminal domains. Here is the coiled coil domain here. Here are the 5 laminin G-like domains here. Okay, and these 5 laminin G-like domains might link up to another integrin molecule on another cell, and hence we have a cell-cell interaction here. Okay, but it's not a cell-cell interaction, it's a cell matrix cell interaction, but we have a cell adhesion basically. This cell is now bound to this cell in this indirect cell matrix cell manner basically. Okay, right, so that's how we're going to link these two cells together, and how the integrin's name as a cell adhesion molecule is well deserved. Okay, right. So what we now want to discuss then is how these integrins are actually going to bind to components of the cytoskeleton. Okay, now, as I was saying, there are 24 known integrins, okay? There are 24 known alpha-beta heterodimers, basically, okay? And of these 24 that are known, 23 of them are going to bind to actin filaments, which are a key component of the cytoskeleton. Okay, whereas the one final one is going to bind to what are known as intermediate filaments, and a key example of intermediate filaments, which we'll come back to in a moment, is keratin. Okay, so this one here is actually going to be extremely important in the skin. So, let me firstly give you an example of one of these 24 integrins, which is expressed in these basal keratinocytes, which is going to be in this group of 23 which bind to actin. Okay, so of course not all 24 integrins are actually found in the skin. Okay, so I'm going to give you an example of a integrin alpha-beta heterodimer, which is one of these 23 which binds to actin and which is found within the skin. Okay, so the example then is alpha-3 beta-1. Okay, so the alpha integrin is alpha-3 and the beta integrin is beta-1. Okay, right, so this is found within the skin and it's capable of binding to certain laminins. So let me give you some examples of laminins that it can bind to. So it can bind to laminin 332, which remember means the laminin where the alpha component is alpha-3, the beta laminin is beta-3, and the gamma laminin is gamma-2. Okay? It can also bind to laminin 511, okay, which means that the alpha laminin is alpha-5, the beta laminin is beta-1, and the gamma laminin is gamma-1. It can finally also bind to laminin 521, okay, which means the alpha laminin is alpha-5, the beta laminin is beta-2, and then gamma laminin is gamma-1. Okay, right. Now, most laminins, just to put this out there because we're going to come back to this later actually, most laminins actually do have as their gamma laminin the gamma-1 laminin, okay, so laminin 332 is unusual in having gamma-2 as its gamma laminin, and we'll come back to why having gamma-1 as your gamma laminin is actually really important later on. Okay, right, so these are 3 types of laminin heterotrimer which the alpha-3 beta-1 integrin, which is found on the basal surface of basal keratinocytes, is capable of binding to. Okay, so let's draw this out then. And then we'll also explore how it's actually going to bind to actin filaments within the cytoskeleton. Okay, so once again, let's draw our integrin alpha-beta heterodimer here. So here are the amino terminals of the alpha and the beta integrin proteins here. Here are the C terminals. Okay, now the smaller one is our alpha integrin, so that's alpha 3 here. Okay, and then the bigger one is our beta integrin, so this is beta 1 here. Okay, and it will be binding to the 5 laminin G-like domains of our laminin heterotrimer, which is one of these 3 here. Okay, so in turquoise here is the coiled coil domain. Okay, then we'll have in blue these 5 laminin G-like domains here. Okay, and then we would have the C terminus there, so I'll just sort of try and squeeze that in there. Okay, and this is going to bind to our alpha 3 beta 1 laminin here. Sorry, our alpha 3 beta 1 integrin here, providing that this laminin heterotrimer is one of these 3 types here. Okay, right, so we now want to see how the alpha 3 beta 1 laminin, sorry, I keep wanting to say laminin, how our alpha 3 beta 1 integrin is going to bind to the actin cytoskeleton of the cell, and this is one of the 23 that binds to actin. I'll talk about the final one, which binds to intermediate filaments, in a moment. Okay, so firstly, let's just have a discussion of the structure then of actin filaments. Okay, right, so we'll start off with the structure of the individual monomer in an actin filament, which is actin itself. Okay, so basically actin is a small globular protein. Okay, so I'm just going to draw a circle here, and this represents an actin monomer. Okay, now there is another name for an actin monomer. Actin monomers are also known as G-actin. Okay, now what does this stand for? Well, the G here stands for globular. So a G-actin molecule means a globular actin molecule. So it's a little actin molecule like so, basically. Okay, now what can happen is G-actin molecules can polymerize together. Okay, so let me show this. Now, firstly, we're going to show them polymerizing into an individual strand. Now, this is not in reality the way the cell does it, but conceptually it's easier to understand if I firstly show you it polymerized into a line, okay, a long strand, and then I show you the 2 strands intertwining to make an actin filament. In reality, you do not build one strand, build another strand, and then intertwine them. Instead, you extend it gradually. Okay, but conceptually this is an easier way to understand it. Okay, so what we're going to do is polymerize loads and loads of actin molecules together, like so, to make a long actin strand, like so. Okay, so all of these are actin proteins here. Okay, now what we're going to do is produce 2 of these and intertwine them with one another. Okay, so we're going to basically wrap these round into alpha helical structures and intertwine the 2 alpha helices. Okay, so let me show you this. So, the alpha helices that we are going to intertwine them into are going to be right-handed alpha helices. Okay, so let me show this. So here is one of these strands. So here is an actin monomer. Here's our next actin monomer. Our next one, our next one, our next one. And at the moment it's coming out of the page towards you. Now it's coiling back into the page away from you. So hopefully you can imagine that this is going around in a clockwise direction. If we turn it round here, okay, that was a bad idea. I don't have enough space to be able to turn this round. There we go. Okay, if we turn this round like here, okay, this is coming out of the page towards you, and then it's wrapping round to the back, it's going into the page away from you, it's coming out again, it's going round in a clockwise direction. Okay, right, so here we come, and then it's going to wrap around again like so. Okay, like so. And it will continue going around, so it's at the front now, and it will continue going around like this, basically. Okay, now what we want to do then is put another strand that that's going to also wrap around in an alpha helical way, okay, also a right-handed alpha helix, but it's going to intertwine. So this one at the moment is at the back, okay, so it's going behind the purple strand here, okay, like so. Then it's going to come out to the front, whilst the purple strand is now at the back. So it's going to actually be at the front here. So get rid of that purple one, it's at the front. Okay, now it's looping back round, it's going to the back, the purple strand is now at the front, okay, it's at the back, and now it's looping back round to the front, so it will go over the purple strand there. Okay, so that's how you're going to intertwine these two actin strands together. In reality, you don't do it like this. You don't build two separate strands and intertwine them together. You extend the two consecutively, basically, okay, or concurrently rather. Okay, right. So this structure then now is known as an actin filament, okay, or it's also referred to as F-actin. Okay, for filamentous actin. So this F here means filamentous, okay, meaning resembling a filament structure. Filamentous, no, not like that. Filamentatus, tamus, it was about to be. Filamentous, right. Okay, so F-actin. So this is one of the key components of the cytoskeleton, basically. You have loads of this. This is one of these strands, basically, that is producing this rigid structure within cells, known as the cytoskeleton. So what we now want to see is how are these integrins, specifically how is the alpha-3 beta-1 integrin going to attach to these actin filaments which are in the cytoskeleton of our cell. Okay, so basically what happens is the larger beta-1 integrin gets a special protein attaching to its cytoplasmic tail here. Okay, and this protein is known as tailin. Okay, so I'll colour tailin in blue here. And now this protein tailin combines to actin filaments within the cytoskeleton. Okay, so let me show this here. So here is our actin filament here, okay, with these two strands that are intertwining in this way, like so. Okay, so I'll colour them in. So here is one of those strands, and here is the other strand here. Okay, right. So tailin can bind directly to our F-actin, our filamentous actin here. Alternatively, it can, well, actually, tailin has multiple binding sites, so it can actually bind to multiple actin filaments, and that's firstly an important concept. So tailin is made up of loads of repeating domains, okay, and these repeating domains are all capable of binding to actin filaments. So here we have one of these domains binding to an actin filament, but we might have another one over here which will bind to another actin filament, like so. Okay, so like so. Here's another actin filament, and we can have actin filaments binding all over the place. In addition, these domains can also bind to another protein, which I'll put here, okay, and this other protein is called vinculin, okay, so this is vinculin, and I'll colour vinculin in orange here. Okay, and vinculin is then also capable of binding to actin filaments. So tailin can either directly bind to actin filaments, or it can bind to vinculin, and then vinculin will bind to actin filaments within the cytoskeleton. But the overall message here is that these integrins are attaching to the actin filaments of the cytoskeleton of the cell. Now, in reality, when you attach these basal keratinocytes onto the laminins, they're not just going to have one of these integrins attaching to a single laminin heterotrimer and then attaching to the actin cytoskeleton. You're going to have a huge number of these things, and these can form quite strong adhesions, okay, and this is what holds the basal keratinocytes onto the lamina lucida. Okay, we'll call it there for this video, and then in the beginning of the next video what we'll look at is this final other integrin, the one that sits on its own, which doesn't bind to actin filaments. So we've looked at an example of the 23, which all bind to actin filaments in the cytoskeleton, and we've seen this alpha-3 beta-1 integrin, which is an example of one of these 23, and it's an example that's actually present within these basal keratinocytes. The one that binds to intermediate filaments instead is also present within basal keratinocytes, okay, and it's known as the alpha-6 beta-4 integrin, okay, and we'll begin our discussion in the next video by studying this integrin and studying the intermediate filaments that it's going to bind to in the cytoplasm of these basal keratinocytes.